Okay, let's start the class. Last time we started discussing how to deal with introduction terms but problem, and we learned the Weeks theorem, which is a very useful can be written as a product of lambdas. Let's write it like this. That belongs to the term C. States with energies smaller than the Fermi network. Is you have just fermions, just particles. Yes, I mean, so alpha particles, you could define, you can define them as different operators. Our A, the A and A negatives are just particles to the vacuum that they call zero. But now the next step that I'm going to take is to convert them to the operators we named C and C. The trick or the idea is that I want to define operators C and C dagger such that for every lambda, C lambda on F will give me 0. Okay? If you like, this is a definition of C. Okay, so this is what I want. I look for some transformation from A and negative to C singular such that the C will act as annihilation operators on F. Okay? And therefore the C dagger will create particles about this function. That we can express them in terms of the A's and A daggers. How do we do it? And you write it here. So C lambda write this. And then you see that each operator No, I have to keep the delta because in general in my sum I have all the u's and lambdas, right? Eventually, remember, I have to compute expectation value of the interaction, which sums over all these terms, right? But you see that because of these deltas, I will eliminate the number of indices, right? Okay? And that's exactly what we're going to do now. Okay, so let's see, what can I erase? I can erase. Now, I also want to give names to, so I have actually now to implement this rule on the two terms that I got that are non-vanishing. The first term, an exchange, and that's why we got a minus sign. This is called exchange or focus. Okay, so what we did, just taking this formula, and I have to see the thetas first. It's a theta of lambda, and it doesn't matter. We already saw in previous slides. Now to compute the expectation value of the entire interaction, let's plug it into the sum. So let's plug it into the sum. First of all, it will be lambda equals mu and lambda prime to mu prime, and in the second term they are exchanged. Okay? So now when I plug it in, you can easily convince yourself that the result will be the following. It's 1/2 a sum over only two indices, mu and mu prime. Both of them are giving a finite contribution only provided that they are inside the Fock state F, okay? Namely that they are with epsilon mu smaller than the Fermi. And then I have the difference between two matrix elements, V mu mu prime, mu mu prime. Here I use the deltas, okay? Minus V of mu mu prime, mu, okay? And now if you look at our lecture of last week, where we classified various interaction terms, there was a direct term, direct type of interactions and exchange. This was the direct, okay, or Hartree. And this was the exchange. So let me call it a Fock, okay? And this is why it's called a Hartree-Fock approximation, because there are two, there are 2 terms, and Now notice that actually in some cases where the matrix elements, these are different matrix elements. Okay, it's important to notice they're not the same. There may be some special cases where they are the same for some reason, and then they're going to cancel each other. But even if they don't cancel each other, this one gives you a positive contribution and this one a negative. Okay? So they say, okay, this is too hard. It's too bad. But if I take the care of operators, yes, to very good expectations are good. The expectation level is just a then the remaining will give me something like, right? That's the but because transfer Q. And each term is related by the Q component of okay, so this is the diagram. Okay. Then there is a line that describes the momentum transfer of something that we can interpret as mathematical particle. And I told you that that particle is actually nothing but so this is actually a photon, it's a Coulomb reaction, a long-range Coulomb reaction. The virtual particle is photons, masses. But that's an interpretation. We don't just run the diagram and describe what I don't do in the equation. So there is the K. There's a momentum transfer because we can think of it like this electron emitted photon with momentum Q, therefore it came out the minus. Okay, so this side describes the scattering from K to K minus 2. Okay? Whereas the electron is taken gain momentum and comes out is taken last. Okay? Within the process, each electron didn't change the speed. Okay? Okay, that's a diagram that describes it and why is it useful? Because it really describes the scattering process where momentum is conserved in each of these processes. Yes? I mean, I put by the way, I put switch here. It's the same diagram. Okay? What matters is what comes out and what comes in to each node. But there is a reason why I reflected it like this, which may be different from what I did in this lecture. You'll see soon why. Okay? Alright, so now I'm taking this interaction term and I'm going to write the Hartree-Fock representation according to the same restriction. And but now these are the quantum numbers that we selected first term have the but denote this by the H. And then I have the factor, which comes with a minus sign, and let's first look at the pattern. With your permission, I'm erasing this, and we're going to write down just the pattern and the pattern. So let me write the pattern. Is I take my sum over k, k prime, q, sigma and sigma prime, v of q, but now I'm using this is the contribution I get. And what can we say about the expectation value of a dagger of this term, this expectation value? What is it? And I remind you, the general is the dagger K here. K has to be inside of the first. It's also a bit, and therefore, so you must do. So let me write. This is theta of k has to be smaller than kf. That's first of all an occupation, which is this theta. delta of Q0 Okay, so because of the delta,
this means we don't have interactions.
What?
The RT term is the term that we don't have interactions.
Yeah, so that's the whole idea about Hartree-Fock, that you replace a pair of operators by the operators remaining here are these, right?
I mean, the RT term is the term of the Hamiltonian without interactions. Right.
No, it's out. So again, the interaction, I'm doing an approximation. Yeah, so the original interaction was the sum over all these terms multiplied by some V of Q. Okay? It was the original interaction.
If Q equals 0, that doesn't mean like
So there is one. There is only one Fourier component. There's one Fourier component. And that's a component Q equals 0. So let me write it down. So it's 1/2 times, actually let me do it a little slowly, but so I still have sigma and sigma prime. Now I have V of 0 and the K and K prime. Sorry, the K is like this, so it's K with K smaller than K. This is an operator. This one has the restriction. Restriction is only coming from K. N is not an operator. It's not an eigenvalue, it's just, yeah, it's the, right, yeah, it's the expectation value, the number of in the field terms, in the ground state. Okay, and that's why, and which is nothing but just counting how many states are below the term. Yes? Okay, so good point, but actually, so you are right. So actually, what is this term describing? It's describing something terrible. Actually, it's infinite. You're right. If I'm unless I'm allowing some, actually it will not really divert because there's a finite size and Q is quantized. Okay, so there is some cutoff, let's say, but actually, what is the physical meaning of V of 0? When you have some potential that depends on space, what is the zero Fourier component? What does it describe? It's just an average, right? Right? When you have some function, okay, in the Fourier series, V of 0 is just the average, okay? So it's the average, and what is actually written here, and what does it describe physically? The Hartree term is in fact describing the following. We are replacing, for each electron, we are replacing all the other electrons by a chunk of charge. Okay, that's what it is, because this is nothing but each electron here interacts with all the electrons. Each of them has charge E, and together it's like you take a charged particle and it interacts with a big block of negative charge. Now this is huge, okay? However, it is compensated by something that is equally huge and has the opposite sign. What is it? Remember, we are talking about electrons in a metal, not in a vacuum. Of course, if you put charges, negative charges in a vacuum, with a Coulomb interaction, it will explode. You cannot, in fact, hold more than a few electric charges. But in a metal, you also have the positive ions, right? The whole material, the stable material is neutral, electrically neutral. So, on the average, within this mean field description, the electrons are interacting with all the other electrons and all the other ions. The total charge of the system is 0. And therefore, the Hartree in this particular example of electrons in a metal with Coulomb interaction, the Hartree part that by itself looks like a huge, in fact, it is like if the system has finite size, notice that what you get here is something that looks like an energy of a capacitor. It's proportional to the square. If I take expectation value, it's just n squared, right? It's something that is proportional to the square of the charge. It's like a huge capacitor. So it's a classical electric energy, but it's compensated by the fact that there is a positive vector. Okay? And because of that, we don't have to worry about the divergences and all that. It is just 0. Okay? If I add the interaction with the ion, it's just yes?
So by this interpretation, why is it interaction only with the electrons below the terminal?
Yes, that's because this is the only contribution. So what again in the Hartree approximation, which is only this term, this expectation value is what determines the weight of each term, and here we have this term. Okay? So we have a non-zero contribution only from electrons that are occupied. Okay? So the occupation of each state is determining whether this electron is there or not. Makes sense, right?
You are summing on the electrons that are below.
No, I'm saying I could actually forget about this. I could put here a theta. Okay, but this theta is just cutting the boundaries of the sum. Right? That's what it does. I just used it, the theta. The theta gives you 1 only provided k is smaller than k absolute value is smaller than k. Okay? Is it clear? I just plugged in this. Right? Okay. Let me try to. I really want to finish this. So now just to complete the story about the Hartree term, I want to show you how you can actually get the expectation value of the Hartree part can be described by a diagram, which is the following. How do I calculate expectation value? I put contractors on each pair of operators. So in the Hartree case, I'm contracting this with this, and contracting in the diagram is like tying the two leads. Okay? So I tie these two leads and these two leads. And what does it mean to tie them? It means that the momentum k minus q is smoothly connected to k. So what does it mean? It means that q must be 0. Okay, so this denotes a k, okay, and this denotes ak prime, ak prime. And q must be 0, otherwise there's no momentum conservation. Q must be 0, and this is v of 0, and okay. This diagram describes the Hartree, the expectation value of the Hartree part. Okay? So just to understand the picture, what is written here is explicitly 1/2 v of 0 times the product of, actually, okay, of course I have, yeah, this diagram is just one such term. It also has a sigma. Prime, and if I want the entire contribution to the interaction, I have to sum over all the k's and sigmas and so on. But this is basically what the diagram is. Okay? It's a graphic way of presenting an equation. Now let's devote a few minutes for the. So I just showed you that chart gives you something trivial. It actually describes just the classical capacitance limit of interacting particles. It's full of interactions. And it's eliminated by the positive background, compensated, so to speak, by the positive background. So it actually does nothing. So this is quite amazing. Why? Because we see that if we look for the corrections to the energy of the electrons in the metal from repulsive interaction, the only correction that is non-trivial in metals is the Fock term. That Fock term is negative. And that's actually true. It gives a correction to the energy. I mean, it's very true. It gives you a negative correction to the kinetic energy. Okay, let's just quickly see what it is. So, I'm erasing this. Okay, so first of all, what is this? This expectation value is a number. What is the number? I'm again going to the original formula, the general formula. It's first of all, it's a theta of k minus q, which means that it gives me contribution only provided that the absolute value of k minus q is below the let's write down what it is. One sigma, because sigma prime is forced to be sigma. And what I'm left with is a dagger of delta. So if k prime is k minus q, k prime plus q is just k. And sigma is equal to sigma prime. And that's what I got. Okay? That's all. And there's a minus sign here. How can I interpret this result? So I can write it as follows. You see that it does look like I have some correction to the single particle energy for each k. So I can rewrite it as minus sum over k sigma of the delta of k, a dagger k sigma l k sigma, where what is delta? Delta is, this is a definition, is the sum over q of v of q, where constrained by the requirement that k minus q has to be inside of the difference. Okay? That's what it is, and this delta is positive, so I'm getting a negative correction to my single particle kinetic energy estimate, which comes from the interaction. Now, if I take an expectation value, it will give me a negative correction to the total energy of the flux C, of the free Fermi energy. And once again, it can be described by a diagram. So now you see why I'm taking it this way. Okay, so this is V of Q, just the operator. Now, to compute expectation values, what I do to compute the expectation value of V4, I basically sum over k and q of the expectation value of this times this. Okay? And the graph, it corresponds to time the length, but not the same length of before. So now we have k, this is k plus q, and this is minus q. This was the original one. So, okay, so again, it's k going to k minus q, k prime, k prime plus q, but I'm tying the length. I'm contracting k prime with k minus q. So this and this. Okay? And this gives me the delta of k prime and k minus q.
talk about two applications of second translation, and we'll start with the most Harvard mode transition, which begin by defining two-side model. Basically, we're saying we have two locations, we can call them 1 and 2, and in those location buckets, whatever, I can insert electrons. I can have electron to spin down, electron to spin up, and electron to spin down, and that's it. Since I hope you all remember Pauli exclusion principle. All right. Now, these two buckets have two special interactions that they can have within them. One, I can take one of the electrons and move it to the other bucket. We'll call this interaction T. Right? And there could be an interaction between the two electrons in the buckets. We'll call it U. It's like U. Basically, you can think about it, for example, two electrons having an electric Coulomb interaction between them. Right? Now, the Hamiltonian of this two interaction, two-side system will consist of the transmission Hamiltonian plus the interaction Hamiltonian. Let's keep it Hamiltonian. Right? So, transition Hamiltonian for the hopping term minus T. We'll assume that the transition has a negative energy sign. Sum over down. Everyone know what this symbol means? Anyone on the sum? Near labels mean that basically says J different than I. They have to be 1, 2 or 2, 1. Right? Equals minus T. A1. Plus the same with the downs, just so you move here. I destroy in one location, we move it to another location, and of course the internal interaction on here, this positive energy. Down. Course, and if you look at the number operator, if you don't remember, look at A. Right. So we have this basic system, and you want to find special cases when we have special properties. The first property that we can think about is conductivity. Right? Now, if this system has 4 electrons, that means 2 electrons in location 1 and 2 electrons in location 2, the system will not be conductive, it will be an insulator. I forgot the word for a second. It will be an insulator because the electron can't move from one location to another. Same thing if we have 0 electrons. It will be an insulator because we don't have anything that carries the energy. Now let's try to look for another case, another special case, when n equals 2. When we have 2 electrons in the system, and I want to prove that if U is very, very big, very much larger than T, then if we have 2 electrons, we have another state where it will be an insulator. So we want to look at a special case. And tot is equal to 2, plus t is much smaller than u. Right. Let's start by defining an operating space when n is equal to 2. Now, before that, let's find our isolate. Why this is an isolator in a spatial case? Yeah, well, it's just intuitively. If you, let's say, we have a state with 2 electrons, one down, one up to different location. If U is very, very large, moving 1 electron to the other bucket and adding the HU term for our overall energy will be extremely costly. So electrons will not want to jump even though the jumping term is negative, because the interaction term itself is much, much higher. Okay, so now instead of saying it in words, I want to actually explore this space. You'll see it again. It's okay. You'll see this feeling again. So the first step to explore the space is to find out all the possibilities that we have, all the basic possibilities for states that we have. So let me just draw 2 buckets. I can have, for example, 2 electrons in the same spin in different location. I will call this the spin polarized state, P1. Of course, this can also be similar state between 2 spin down states, with 2 spin down electrons. Now, I can have a similar state, opposite spin, down. I would call this the single occupancy state. Right state is S1. Next up, we can have the exact same thing, but opposite location of the spins. And I'll call this S2. Finally, I can have what I call a double occupancy state. We have 2 electrons in opposite spin in the same location. I will call it D for double occupancy. Of course, there's a similar symmetrical one, D2. Right. If I want to translate this to general Fock state, I can define Fock state that follows down. Let me just write it in better location. And 1 up, and 1 down, 2 up, and 2 down. Right, with this writing I can represent all of the different states. For example, P1 would be equal 1, 0, 1, 0. And S1, for another example, will be equal to 1, 0, 0, 1, and so on and so forth. All right.
Okay.
You have a question?
Yeah, just trying to figure out the rotation.
N1 up, N1 down, N2 up, N2 down. Basically, I'm counting each electron here. and the direction of each electron. All right. So the next step to like analyzing the system is finding the eigenstates. We have two eigenstates which are very easy to spot. P1 and P2. P1 and P2. If let's say we look at P1 for a second, it cannot have that transmission, the how do they call it? The hopping Hamiltonian will give us a 0 because you can't transfer a up spin to another location with another up spin. And the interaction Hamiltonian will also give us 0 because each bucket only has one electron. So these two are two eigenstates. And since we have another 4 vectors here, we know that we need to have another 4 eigenstates. Now, it's so hot here. Now, I can like take these 4 and transform my Hamiltonian into a 4x4 matrix and solve it, and it will be fine. But if, let's say, we'll try to scale this problem up to a 6x6 Hamiltonian or a 10x10 Hamiltonian, it won't be so easy. So I want to try a different method.
Maybe you can guess. Maybe you can guess.
I can try to guess it, but I want to try a different method that heavily relies on the condition that I put up here, where t is much bigger than u. Smaller, thank you. All right. Yeah. Instead, I will take this assumption and make ht some source of small perturbation. Using this perturbation, I will make some canonical transformation to the Hamiltonian, and then I will take the Hamiltonian and project it on the S1 and S2 space. Now the last step is not so trivial, but I'll say it's okay, it's a good approximation, because if u is much bigger than t, those two states, while having the interaction Hamiltonian contributing to the energy, will cost a lot of positive energy. So we can assume that the ground state, the lowest energy state, will be composed mainly of hopping terms, or states that can do that has some hopping option and no interaction option. So again, I'm going to consider t to cause small perturbation, do canonical transformation using those perturbation, and then project our Hamiltonian, the resulting Hamiltonian, into the S space. Okay. Before we start, I said we want the final step would be projecting the S space. So let's, before we do the entire process, talk about projection operator. So what's a projection operator for the S space? We'll call it P of S, and I want it to preserve the S state, but block the D state. Alright? For example, I want PS of 1, 0, 0, 1 to return 1, 0, 0, 1, but PS of 1, 1, 0, 0 should give me a 0. In this house, in this course, we believe in the propaganda that every operator can be represented by creation and annihilation operators. But we want to preserve the number, the count, the electron count. So every annihilation or creation operator should be conjoined with its pair. So if I have an annihilation, if I have somewhere an annihilation operator, I know there should also be a creation operator. So basically, what I'm trying to say, if we must have an annihilation and creation, this operation will probably be built by the number operator.
Can I ask a question?
Yeah.
You require that the eigenvalue will be 1, or just it will be a consequence of the operator we choose?
This is a projection operator. This is the definition. It'll take whatever combination you give it and project it into a space defined by S1 and S2. If it projects something to the space of S1 and S2, it must preserve S and destroy your other axis and zero out your other axis, which is the D's.
And the eigenvalues are of 1 in the basis of S1.
In this basis, yeah, the eigenvalue is 1. And again, remember, projection should not give you a multiplier or something. It just should tell you you have some state. What the part of this state is in the S spaces. What's the part of it in S spaces? So the eigenvalue must be 1. It's a projection. All right. So we know that it has to have some n, and we have 2 electrons in this state and 1 electron in the S state. A good guess, I won't do all the math to get here, just give you the answer, would be sum over I, and I minus 2. Right? Now, seeing why this works, might be, sorry, this is operators. Now, if we have at this state here, one side has 0, so the first term will cancel it out. The other bucket has 2, the second term will cancel the other bucket. But if we have an S state with n equals 1 and n equals 1, there will be just 2 terms here of 1 times 1. Minus. Sorry, this is 2 minus. Sorry, this is my mistake. This is 2 minus ni. So let me just do an example with this one again.
But also the P is not 0 under this projection.
Yeah, but P is already a ground state, or P is already a zero energy state, the eigenstate of the Hamiltonian, so we found it and then we put it aside. Because, yeah. So, we have PS equals 1 over half Ni 2 minus I 1 0 0 1 equals 1 over half of 1 2 minus 1 plus 1 2 minus 1 equals 1 times the 1 0 0 1 equals 1 0 0. Okay, similarly, you can do the projection operator on the D space. Let's do a small d. Should be equal to 1 over half. So I minus 1. This one you prove in your homework, so I'm not like, writing down the example. All right. So now that we have the projection operator, is there a question? Now that we have the projection operator, we can start the transformation that we talked about earlier. First of all, I would like to define an operator. f equal 1 over du of ps h of t pd minus pd ht ps. Right? Might seem a little bit arbitrary to define this operator, but let me give you a little bit of intuition. Let's look at one of these terms. Let's say this one. What did it describe? We start with a D state, double occupancy state, and then the hopping term of the Hamiltonian, which basically means we take one electron from one space, move it to the other space, and it will automatically transform into an S state. And exactly the other way around works in the second part of this equation. So this, before that, h of t here as a factor of t if you will open it outside. Overall, the factor of f outside will be actually 1 over u, which is a very, very small factor. So we can look at this operator as something that describes our perturbation. Very, very small chance to move from D to S or from S to D. Very, very small chance to have a hopping happening. And in your homework, you will show that f, the commutator f in HU equals to 1 over T HT, which is the actual reason why we picked this operator. But again, you'll show it in your homework. Okay. Now we take this operator, which somewhat describe our perturbation, and we want to use it to do a canonical transformation of H. Now, take H time equal to that e to the minus T F H E T F. All right. Yeah, it's winter. Why is it so hot? Okay. This form of transformation will not. The course doesn't really touches this transformation, but usually when you want to transform an operator by a different operator or Hamiltonian, you use this form of equation. Again, it's not in the material, so for now, this is just the canonical transformation for f. But you'll probably see it in different quantum courses if you take it. This Hamiltonian can be, this equation can be opened using the Schrieffer. I hope I'm probably not saying it right. Schrieffer-Wolff equation, fermion equals to H minus T F H plus T squared divided by 2. Technically 2 power, okay. F H TV demu. This is like a this is a commutator inside the commutator if you can see it, but it's yeah. It's called the Schrieffer-Wolff transformation. It's just a solution for this double exponent.
It's like an infinite series, like
yeah. There's small terms here.
yes.
Yeah, plus. Now, let's take, since t is very, very small, let's take this up to second order in t. So h tag is equal q T minus T F H U minus T F H T plus T square divided by 2 F F H U, and I'm not taking this the second term, the second order in T with HT here in the commutator, because HT has another factor of T inside, and it will be effectively T to TQ. You only want to take up to second order. Okay. So using this equation right here, we know that. Sorry. Using the equations that we found, that you found, here before, T times the commutator of F and HU will be equal to HT. So this term right here is 0. And this term right here will be T divided by 2. T divided by 2 F HT. So overall, tag equal HU minus T divided by 2 F H. So we're done with the canonical transformation. I'm not going to open this commutator right now. Now we only have to transform this into, project it into the S space, the S occupancy space. Right? In order to transform something to the S occupancy space, we need to multiply it on both sides by the projection operator. And now we can notice that, yes, HU PS equals to 0. Because every term in the in the S occupancy space has 0 in location interaction energy, since there's only one electron in each space at a time, right? So we only have left with F HT times minus T divided by 2, and all of this PS. Now F HT, do it really quickly, equal to PS HT PD HT minus PD HT PS HT minus HT PS HT D plus HT PD HT PS. thing I forgot, one thing is this. First thing, notice that by projecting into the S space, which would be the space, will be approximately the space where our ground state exists, we sort of erase the excited state. We remove two axes, the 2D basis space that we can evolve, and we're only left with the space that is spanned by S1 and S2. So we, by definition, gain a lot of knowledge on the ground state, but we lose a lot of knowledge, or basically all the knowledge, on the excited state, which will be mostly made up of these states. So this is a one negative of this equation, of this method. Second thing that we need to notice is that PS times PD would be 0, since you can project into two different spaces at the same time. Alright, so if we take this equation right here, this term, which starts with a PD, will vanish, and this term that ends with a PD will vanish. And in addition, PS will just be equal to PS. Projecting twice into the same space does not. The same as projecting once. Okay. Overall, PS F H T S equal to 2 divided 2 times PS HT PD HT. And of course, PS hashtag PS equal to minus over U P S HT PD HT. Now, this term right here in the middle, I would love to develop this lengthy calculation, but unfortunately it's in your homework as well. So just be equal to t squared 1 plus sum over sigma tag A1 dagger sigma A2 dagger sigma tag times A1 sigma tag A2 sigma. Using, again in your homework, using this solution and putting in this equation right up here, you'll find that PS H tag PS equal to J is 1 is 2 that's 1 over 4th where J is equal to 4 t squared divided by U equal to 0. Now, even without finding the constant, you can say a few things. Well, it's one major is that when we have very low energy, low temperature, this positive J indicates that this is an Hamiltonian of anti-ferromagnet.
What's the definition of SI?
It's the spin operator.
And you get it from the A's.
Yeah, you saw it in last tutorial and in the last homework. And yeah, best overall, S1 and S2, with the fact that the J is positive shows that this is an anti-ferromagnet, and notice that the interesting part, what I think is the interesting part here, is that it has a very, very clear definition for its magnetic order, although it has no spin-to-spin interaction at all. But it still forces us into an anti-ferromagnet, and if we'll expand our model to have more than 2 locations, 3, 4, and so on, this is not a calculation that you see or have to do. The overall equation will be Mn Sm S. It will show us another simple an anti-ferromagnet. Long range. Well, this was the most Hubble chapter.
So, like, this canonical transformation, right?
Yeah.
So, and you're claiming that it doesn't change the physics of this canonical transformation?
Not really. I'm claiming that this is basically like a perturbation theory, just general perturbation theory. I'm just transforming this Hamiltonian, keeping it admission and whatever, by making like transforming it with an operator that does slight changing to the states. So that's all the canonical transformation says. It has some sort of small transition that can happen, a very minor transition, and do a transformation based on it. But like, does that answer the question? Or do you want to be more specific?
Like, why this canonical transformation doesn't like alter the states dramatically, or it's not perturbative, like what? You have a different Hamiltonian,
I don't have an answer off the top of my head, but let's talk about it after class, right? It's a good question. Okay? Might actually finish a little bit early. Next, now we saw an application of how to use a few small tricks to solve a slightly complex problem. Now, instead, I wanted to take you in a different direction with second quantization and show you a trick, something, in order to find an expectation point. Basically, a general usage method of working. So, Rick's theorem. Right. Before we can go to the theorem itself, let's assume we have some set of operators, A, B to Z, where each operator here is either a creation or an annihilation operator. For example, A, B, C, D equals n of k, el dagger, am dagger, an. want to define the notation of normal order. Let's say, for example, the exact same set of operators, dagger and dagger n. Normal order notation would just say all the creation operator goes to the left, all the annihilation operator goes to the right. Okay. Now, you just need to emphasize this. This notation n is just a notation. It's not a function or an operator. This is just, I'm saying, look at this set of operators, they are in normal order. And we're working with both ones for simplicity. Okay.
So we don't need to keep up with pluses and minuses.
Yeah, it's simple. You can develop this entire thing for Fermion, but you need to be more careful. What you can do with you following the exact same step that I'm doing in this tutorial.
Just using the minuses.
Yeah. Okay. So I said again, n is not an operator or something; it's just a notation. But let's see how we can go from the original form to the normal order, just to make things clear. So, AK, AL, AN, AN. So I want to take all the creation operator outside, so I'll use the commutation relation. So, commutation relation AK, AL, dagger, AN, dagger, AN, plus AL, dagger, AK, AM, dagger, AN. I'm not putting in the value of the commutator on purpose. I'm just doing it like this. But it's the same thing as writing a delta. Okay, now I need to move the m outside, so to the left. So it will be AK, dagger, A n dagger n. Plus AL dagger AK AM dagger AN plus AL dagger AM dagger AK AM. And notice this right here is the normal order of AK A dagger and dagger. Between the original operator and the normal order operator, dagger, n minus n, okay, dagger, dagger. Oh, I hope you all forgive me that I got tired of writing hats. I already care about it. Fold the relation. Dagger, and dagger AN plus AL dagger AK AM dagger AN. Now I want to define a very useful notation. Another notation called the contractors. A, B, contractor equals AB. minus normal order of A, B. Very similar to what we have up here, just with two operators. Now, if A and B are already in normal order, this will be 0. And if it's not normal order, it will be the commutation relation. So, using the new notation, I can change the commutator here with contractors. So, K, AM dagger, AM שווה ל-normal order of the same, plus AK, AL dagger, AM dagger, AM, with the contractor here, and another AK, AL dagger, AM dagger, AN, with a contractor with a longer range contractor. If we're talking about the fermions, here would be a location where you need to notice that since you move it twice, there will be two minuses with plus inside. So for now, we move it into boson, so we don't have to count the number of rotations that we need to do, because each rotation in the fermion has a minus. But, keep it in mind when you need to work with normal orders and contractors with fermions. So now that we have, wait, one second. Before that, notice that this contractor is a number, this contractor is a number. So we have a creation and annihilation operator, and a creation and annihilation operator. Both of these also in normal order. So I can take this normal order notation and move it to take up all the entire equation.
I think you added an extra dagger than AM.
That's a plus. That's the risk of doing quantum. Right. So now we can finally, after defining all of this notation, we can finally go to the theorem. Now I'm not gonna give you the theorem and then immediately prove it. I'm gonna give you the theorem. We're gonna use an example, find out what's the usage of the theorem, and then at the end I'm gonna prove it. Yeah.
Don't you have also the contractions of all the operators, like two contractions?
You're skipping ahead. That will be in a second. Here, I'm not using the theorem yet. I just got to this location by doing normal process and defining a contract. Okay. So the theorem, I'll erase and then I'll talk. That's smarter. So the theorem goes as follows: A, B, any set of operators A to Z equal the normal order of A, B, all the way to Z plus all contractions. Now, all contractions means all the possible bridges that you can build. Alright? For example, if we take A, B, C, D, the theorem says that it will be equal to normal order of A, B, C, D plus C, D here plus D, C, D here A, B, C, D. Here. I'm not going to write all the first, there was only one contraction. It's too long. Plus A, B, C, D. There's two contractions, yes, so there cannot be more than one contraction in this normal order writing. Plus A, B, C, D. Plus A, B, C, D. Usually you don't write contraction from below, but I do because it's more comfortable for me. Usually you only write contraction above, but if you know what it means, you know what it means. Right? And the last terms, the last three terms, where all of the terms have a contraction on them, we call those the fully contracted terms. Those are some terms with contractions in them. These are the fully contracted terms. Okay. Let's use the theorem on our previous set of operators just to see that it works for this specific example. So, AK, AL, AM, AN equals N of K again, N again, AN plus M and first contraction plus K M N N contraction plus A M N. Okay. Instead of writing all the terms, I go one by one because all the extra terms will zero out. So I'll just go one by one and we'll see that they zero out. So first of all, AK and AN, two annihilation operators. They are by definition in normal order, so it's zero. The contraction is equal to zero. Now, if we start with AL, for example, go for AN, it will be in normal order, same as going to AM dagger, so it will also be zero. Now, same thing with AM dagger and AN, it's already in normal order, and when we are in normal order, contraction is zero. Now we have to do the fully contracted terms. Start from the most simple one. This contractor is not in normal order, so it's not zero, but the second one is in normal order, so it is zero. Another example. AK with AM dagger and AL dagger with AN. Again, the second contractor is in normal order. Now, taking AK with AN and AL dagger, AM dagger, both of these contractors either only have annihilation operator or only have creation operator, so it's again zero. Okay, good example. Very fun, very fun, very fun. In the end, so again, there's no more terms here. And we'll get the exact same answer as we did before. Okay. Now, what do we do with these contractions and normal orders and blah, 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 blah? Well, if you want to calculate the expectation value, the set of operator A to Z will be equal or all fully contracted for each term, for each fully contracted term that isn't equal to zero, we add another one. For example, if you want to find the expectation value of this operator, it would be 0, because it doesn't have any fully constructed terms. Of course, in this specific case, we can simply see that an annihilation operator on the left will immediately destroy the vacuum space. Oh wait, I forgot to add that the states here is a vacuum. If we do an expectation value of the vacuum of a set of operators. A set of operators find an expectation value on the vacuum. Okay. So how do we, so a general method to approaching large set of operator, the expectation value for large set of operator. First of all, look, let's say 1. Look if there's an annihilation operator at the end or a creation operator at the beginning, since it will be automatically be 0. Second thing that you should do is to check if the number of annihilation operator is equal to the number of the creation operator. Since the bracket, the quantum states, and let's write n, and n, since they're orthonormal to one another, if you annihilate a particle, you also need to put it back for the final multiplication of the two states. The vector multiplication here will not be equal to 0. So first of all, you look for annihilation operator on the right or creation operator on the left. Then you count how many creation and annihilation operators you have. And then third, use big theorem. Use big theorem to find all the non-zero fully constructed terms. That's it. That's how you go find expectation value of a set of operators on the backend. Yes?
But this is only the expectation value of the ground state, right?
Yeah, I mean, if you define a vacuum as a ground state, yes. In the next tutorial, we'll use a we'll use this on a non-trivial vacuum state. So yeah, weak theorem can be expanded, but you need to be careful. Of course, you can also try to find a special solution without the vacuum itself. But this is like the most the most basic usage, the main usage of it. All right, so we did an example. We found the usage of this theorem. Now it's time to prove it. Go ahead. We're going to prove it by induction. We'll define the omega n, some set of operators with the length of n. The first step, step 0, in the induction process, checking it with omega equals 2, AB. Now it's obvious that if A, B are in normal order, the expectation value will be 0. And if A, B are not in normal order, we only have one fully constructed terms, and it will be equal to 1. So let's write it. Let's do it a little differently. Equals. Remember that this is the theorem we try to prove, not this part. It's right here. Equals to n dB plus contracted. Again, this is trivial. If AB already in normal order, it will just be AB equals to AB. If AB is not in normal order, we'll have this, which will be the rotated term, BA, plus the commutator of A and B. This one is trivial. So, 1. we'll assume that for n minus 1 theorem works. Theorem
n minus 2.
what? No, n minus 1.
No, the number should. You don't assume it's even number of operators.
Notice that this, while an odd number of operators will give us an expectation value of 0, but this is the theorem that each set of operators can be open to normal order of the operator plus all constructions. So it can be with odd numbers. So for n minus 1 it works, and we'll define our n omega n to be a b all the way up to z, when b up to z will be omega n minus 1. Okay. So since the theorem works for n minus 1 operators, I can use the theorem on the right side of this equation. Equals to a times normal order of b to z plus all instructions. This normal order, as we said before, is just a notation. I can open it up to normal order of b to z, and normal order of plus normal order of all contractions. So equal to a times normal order b to z plus a times normal order of, just gonna write all because I'm lazy. Now, I'm gonna leave the original theorem up here, just we'll have it. Okay. So now we have two options. Either A is it you need me to read it, is it like how to read? It's okay? Okay. Now, if A is a creation operator, it's already in normal order and we're done. Right? If A is not a creation operator, it's an annihilation operator, I can try to take it to the right side and force it to be in normal order. Okay. So we have n equals to n b z times a plus commutator of a n b z plus n all contractions a plus the commutator of a and all contractions. Right? Well, I just moved a to the side. Now,
how you got fault? How you got fault?
Because we have the terms that we rotated, and then if we rotate, and then if we switch the order of operator, we need to add commutators. Okay. Now let's look at these two left terms. The first term right here is the normal order of A to Z. This term right here is the normal order of all commutators that don't involve A. Okay. And now let's look at this commutator. This contractions that doesn't involve A. Sorry, yes. Now let's look at this term, the first term on the right. A and B to Z equals n normal order of AB contraction Sorry, let me just do it a little bit differently. B C to Z plus B AC D to Z plus B Y MC Z. I did two different actions here. First of all, the equation that you see down here, it's a known equation for a commutator of multiple terms, of one operator with multiple terms. And since all these commutators are just numbers, and all of these operators are already normal order from here, I just expanded the normal order to apply to everything. Right? Now this A and B is just a contractor. So is A and C, so is A and Z, just a contractor. Be equal to N A B contractors, so Z plus A B C D Z plus A B Z contractors plus. So basically, this term right here is all the terms which have a contraction with A, only one contraction with A. Similarly, we can do exactly the same thing here, exactly the same thing in the second term on the right as we did on the first. It will give us all the contracting terms which have more than one contractions and which are contracting with A. So overall, we have all contraction that doesn't involve A, all contraction that has all the terms that have only one contractions and involve A, and all the terms that have more than one contraction and involve A. All these three together basically have within them all the contractions that we can possibly make. So overall, omega n equals n of A Z plus all. And this is a proof of the theorem. Any questions? The last step was like a little bit of a jump, so it's okay. So I understand there's a bit of a question why this would result in this.
Can you remind how the bracket is related to the contraction?
Contraction. I'm just going to write the equation for contraction again.
Okay.
I'm going to contraction A and B equals AB minus A. Sorry. Normal order. So if AB is a normal order, it's equal to 0, and if it's not a normal order, it's just the commutator.
Okay.
So we can just say overall commutator is a contractor because we assume here that A is a relation operator. Because if it's a creation operator, we're done in this step. Any questions? I thought we won't have time for everything. Okay, I could have actually added another chapter. It's okay. This is it. That's all. Again, remember these 3 rules, 3 steps. This will make every like expectation value on the vacuum very, very simple to calculate. Look for an annihilation operator at the end, or creation operator at the beginning. look that there's an equal number of creation and annihilation operator, and then in the end use weak term to calculate the actual part. The first two steps are like filters. Thank you. Homework will be another set of homework uploaded today. Don't worry, there will be a lot of time to submit them, and they're not going to be that long. That's it. Oh, that's it. Have fun. The tutorial notes are already up. Thank you. Thank you.
כאילו הטענה שזה קנון טרנספורמיישן, אבל לא יודע למה זה הטענה. וקנון טרנספורמיישן שזה אחד שמשנה את ההמונטוניה, ואז זה הגיוני, אבל כאילו משנה את המשוואות ההמונטוניה.
שים לב שזה משנה לך אולי את הצורה של ההמונטוניה, אבל בעיקרון, אם נסתכל על מה ש-F עושה, הוא לא באמת מזיז לך את ההמונטוניה, הוא רק אומר שיש לך מצב שהכל בצורה אקראית, זה סיכה מאוד ארוכה, משתנות מ-S ל-D. זאת אומרת שהוא מכניס לך איזה perturbation, משהו perturbation בסטייט עצמו. הוא לא משאר לך את ההמונטוניה. אני אנסה פה יש דרך יותר טובה.
כאילו, מה שנכיר, כאילו,